Hi, my name is Thomas. Welcome back to the QC lecture series. This will be our third lecture, lecture 3 on basic Qiskit. We went ahead and just decided to record this separately from the live event. We'll do the same thing for the fourth lecture, just because it's a little easier to handle than having to record it while also doing the event live. So as you may know, this one is on basic Qiskit, and 2 weeks from now, March 1st of 2023, so the Wednesday of week 8, we'll be having our lecture 4 on more advanced Qiskit. Now, sort of as a brief overview of what we're going to cover today, we're going to talk about what Qiskit is. There's going to be some slides going over how to make an account with IBM in order to use their quantum computers. This isn't mandatory. You can, well, you have to make an account in order to use their quantum computers. You don't necessarily have to use their in-browser IDE, which is called the IBM Quantum Experience. But the nice thing about it is that you don't have to worry about setting up, like, for example, a virtual environment and installing Qiskit locally. It just has everything pre-installed there. So we'll have some slides that kind of direct how to do that, but I'm not really going to go through them in this video. The slides will be posted to our Discord along with the notebooks, the Jupyter notebooks that I'll go through later, and this recording. That'll be posted in the archive section of our Discord. So if you would like to have sort of a walkthrough of how to make that account, you can just find the slides there. Okay. What is Qiskit? So broadly, Qiskit is just a quantum SDK for Python that's made by IBM. So it's not the only one. You can do quantum programming with a few different libraries, but it's one of the most well-known. And it's nice because IBM has been in the quantum game for the longest, and if not the longest, then close to. So their library Qiskit is quite well documented and has a lot of features. So some other examples that you might use are there's one called Cirq, which is by Google. There's PennyLane, which is by another company, Xanadu, and then there's an Ocean SDK that's by a different company, D-Wave. And broadly, a lot of these sort of do all the same kind of things. And once you learn one, it's pretty easy to transition to the other. So we're just going to start talking about Qiskit because it's the sort of prototypical example. Okay, so here's the slides on how to make an IBM account. I'm just going to kind of skip through these quickly, and we'll get to the rest of the content. Okay. So, as you may remember from the second event, the lecture on quantum mechanics, at the very end of that lecture, we talked about a specific example of a quantum system, namely a qubit. So we're going to really hone in on qubits for the last 2 lectures here because they are the quantum sort of system that's at the heart of our quantum computers. So even if you didn't understand everything from the quantum lecture, that's okay. We just want to make sure that we understand qubits, at least at a very high level. So broadly, a qubit is just any 2-state quantum system. So you can physically make a qubit in a lot of different ways, just like how you can physically make a computer in a lot of different ways. Traditionally, computers are made with bits that are low and high voltage. That's like 0 is low voltage and 1 is high voltage. But if you look up on YouTube, you can find videos of people making computers out of water, and it's like water pressure, or any sort of thing you can think of, as long as there's a 2-state system. And similarly for qubits, you can make them out of anything as long as it's a 2-state quantum system. Now, the interesting thing about qubits is, unlike regular bits, they can be not only 1 or 0, but also in some arbitrary probability distribution between 0 and 1. So that's kind of a lot of big words to break down what we mean. You can imagine a 50-50 distribution, which would be like a fair coin. So you have a 50% chance of being in a 0 state and a 50% chance of being in a 1 state. There's a 70-30, which would be, you know, sort of like a weighted coin. And you could imagine a 100%, 0%, which is really more just a classical state. You're 100% in one state and 0% in the other. These are not the only options. These are just a few examples. Any kind of probability distribution, any splitting of the percentage between 0 and 1 you can think of is a valid superposition. And superposition is the word that we use in sort of the business to talk about this kind of arbitrary probability distribution. If a state is split between 0 and 1, it's in a superposition. The other interesting thing about qubits is that when we measure them, we don't measure a superposition. We only ever measure either a 0 or a 1. And we call this a state collapse. So just like how when you have a coin, there's a 50% chance it comes up heads or tails, but once you flip it, it's only either heads or tails. It's not both. A couple other interesting things that aren't going to be super important for what we talk about in the next 2 lectures, but are just sort of good to know about qubits. In practice, we can't really store them indefinitely, just because the hardware we have now is not very good. So one of the longest times that people were able to store a qubit, which basically just means make a qubit either a 0 or a 1 and then keep it as that state, was about 1.5 hours. And that was only one qubit, and it was extremely isolated. In quantum computers, where you have a bunch of qubits and they're not isolated at all, the coherence times are a fraction of a second. And we call this like sort of where the state decays from some known state that we put it in to really just any random thing. We call that decoherence. The other thing to know is that, and this is kind of the big reason that people think quantum computing might surpass regular computing, is that we can chain multiple qubits together and kind of connect them in such a way that when we measure one qubit, we actually measure multiple qubits at the same time and cause sort of like a chain collapse of qubits. And this is called entanglement. And again, we're not really going to get into that too much. The math gets pretty complicated, but it's just sort of good to know that is there. Okay. As a last little bit of review of qubits, I just want to show you a couple pictures of visually what these states might look like. So if we want to visualize what the state of a qubit is, we use something called a Bloch sphere, which is just this sphere here. And the state of the qubit is just an arrow that points to some location on the Bloch sphere. So we say on the left that we have an arrow that's directly pointing up. We call that the 0 state, and it's 100% chance we're going to measure 0 and 0% chance measure 1. These little parentheses here is percentage of measuring 0 and percentage of measuring 1. And then on the right, you see the 1 state where the arrow is pointing directly down. We could also have something in the middle. We have 2 different 50-50 states. They're both 50-50 in terms of likelihood of measuring one or the other, but they actually are orthogonal states. They're different states. But the way that they're different has to do with something called phase, which is really just like a math thing that's not super important to us. So for as much as we care, we can really just think of these as both being equal probability superpositions. And then lastly, I just have a couple examples of what some 70-30 states might look like. Both 70-30 for 1 and 0 and 70-30 for 0 and 1. Okay, so that was just kind of a lightning review of qubits. If you feel that you're still not super solid on them, I would encourage you to go back and look at the recording for our lecture 2 on quantum mechanics. We go into more detail about qubits and some of the math behind them towards the end of that lecture. And then there's also resources both on our Discord as well as just online that you can find that go over qubits pretty well. So let's just jump ahead and start getting into more programming stuff, which is specifically, what is the syntax for Qiskit? How do we actually program it? Okay, so as we go through the syntax, what I want you to keep in mind is this picture of a quantum circuit here. So this quantum circuit is sort of the end goal of all of our Qiskit work. What we're trying to do is make a quantum circuit that looks something like this. The Qs here represent qubits. these C's are really just like regular classical bits, so the thing that we're all used to. And then there's these things called quantum gates, and then there's these things called measurements. And we're going to break down what all this means. But it's just good. I wanted you to see a visual before we actually talked about all of these things individually, what the end product is going to look like. And I'll show this again after we talk about all these individual pieces, and you can kind of see how it all comes together. Okay, so the first thing that we have to do when we want to make a quantum circuit is we have to make a quantum circuit variable. So that we do that with the Qiskit constructor function, just called quantum circuit. And it takes two parameters. N is the number of qubits. We have to pass it this parameter. And this is just how many qubits do we want our quantum circuit to have. If you're running on a simulator, then you should check to see how many qubits your simulator has before you use this. If you're running on a real quantum computer, same thing. You should check to see how many qubits your real quantum computer can handle before you set this number. We'll get more into the difference between simulators and real quantum computers in our lecture 4. But for now, I would say usually just a few qubits to get started is a good number, just to mess around with things. And then M is the number of classical bits. You don't have to have any classical bits, but it's useful because when we go to measure stuff, so when we actually want to get data out of our quantum circuit, when we want to do some computation, we have to have a classical bit to store each measurement in. Generally, the most number of classical bits you would want is equal to the number of qubits. So if you have 5 qubits, you would want to have at most 5 classical bits, but you may also want to have fewer if you're not going to measure every qubit. But as a rule of thumb, you could just start out by saying, setting the number of classical bits to be equal to the number of qubits. So we've made our quantum circuit, we've made our object, which is sort of the thing that we're now going to be adding all of our gates and measurements to. But how do we actually do that? So what we do is we take the name of our quantum circuit object, QC, and we just call a method function on it, and it just .gate, where gate stands for whatever the name of the gate is. And then that gate will take some arguments. And all it does is it appends that gate to the end of sort of this queue of gates that are going to happen. So if we jump back to the picture real quick, you can imagine that each qubit is sort of a queue of operations where you go from left to right, and you do the leftmost operation first, then the one directly to the right of it, then so on and so forth. And whenever I add a new gate to a qubit, so if I were to add, let's say I added a gate here to qubit 0 after this H gate, it would just show up right here. Of course, what we've actually done is added a measurement after the H gate. So in terms of the arguments that we have to add to our gate, there's really, for now, we're going to talk about 2 different types of gates, rotations and C-naughts. Rotations only take 1 argument, and the argument we give it is the qubit we are applying that rotation to. And we'll get into in the next couple slides what rotations and C-naughts are. But I just want you to know that rotations take 1 argument, and it's the qubit we're applying them to. C-naughts take 2 arguments, a control qubit and a target qubit. And again, we'll get into what that means in the next few slides. So quantum gates really are just matrices that we're applying to our quantum state vector. If you remember back to lecture 2, we sort of said how matrices in linear algebra, we just think of them as being operators in quantum mechanics. We just use a different word for it. And really the only reason we do that is because sometimes these operators can be infinite dimensional. And if you call it a matrix, it implies that you can write it down and do some linear algebra. But of course, if you had an infinite dimensional matrix, you can't really write it down and feed it into a computer. So we just like the term operator instead, but it's really the same thing. Now we're going to talk about a couple different types of gates, single qubit gates, which for us are going to mean rotations, and 2 qubit gates, which is going to be our C-naught that we saw in the last slide. And then there's another thing that sort of acts like a gate in terms of syntax, but it's very much different in terms of what it's actually doing, and that's our measurements. So I'm going to call them measurement gates, but just keep in mind that they're really not gates per se in the same way that the other ones are, but they're treated the same way by Qiskit in terms of the syntax. Okay, rotations. So the reason they're called rotations is pretty nice. It's just because they are rotating your vector around the block sphere. So remember how we showed that we can represent our state for a qubit as a vector on our block sphere, and rotations are just rotating it around some axis. So in particular, we're going to talk about 3 rotation gates: the X gate, the Y gate, the Z gate, and the H gate. The X, Y, and Z gate all do very similar things. They rotate you 180 degrees around their respective axes. So X rotates you 180 degrees around the X axis. In particular, they're rotating you counterclockwise, as you can see here. But because it's 180 degrees, it doesn't matter. You get to the same place. Now, the X gate for us is sort of the quantum gate equivalent of the NOT gate. Which is to say that it takes our 0 state to our 1 state, and it takes our 1 state to the 0 state. So it's just like in classical computing, we have something called a NOT gate, which just flips our bits. If you input a 0, you get out a 1. If you input a 1, you get out a 0. And the X gate does exactly that for our quantum bits. The H gate is a little weird. It rotates us 180 degrees around this diagonal line, Z equals X. So it's sort of a diagonal line that's in this plane here of this circle. And it's the diagonal line between the Z and X axes. And really what that means is that it puts us into an equal superposition. So we're going to use the H gate a lot whenever we want to take advantage of equal superpositions. For example, it takes our 0 state and it rotates it around this line, 180 degrees, and puts us into one of our 50-50 superposition states. So C naughts, or as they're called in Qiskit, CX, are sort of a special 2-qubit gate. And the reason that we like them is because it entangles 2 qubits together. And more mathematically, what this means is that we're mixing the states of the 2 qubits into a single combined state that we can't really unmix. But the better way to think about a C naught is it's sort of like an if statement in regular programming. So the control qubit, which is the qubit that has this little dot on it, if the control qubit is a 0, then we do nothing to the target qubit, which is the qubit that has the plus. So if we measure the control qubit and it's a 0, then we do nothing to the target qubit. If the control qubit is a 1, if we measure the control qubit and it's a 1, then that means we apply an X gate on the target qubit. And so because the state of qubit 1 is tied to the state of qubit 0, and vice versa, we have now entangled these 2 qubits. That's sort of the classic definition of entanglement. Sorry, I accidentally jumped ahead there. The important thing to keep in mind here, and this is part of the weirdness of quantum, is I was careful to say that if we measure the qubit 0 as a 0, so I could have, for example, an H gate in front of this, and this is really how you make entanglement. I could have an H gate in front of this C naught here on qubit 0, and that puts my qubit 0 into a 50-50 superposition of 0 and 1. And that means that there's a 50% chance that qubit 0 is a 0 and a 50% chance that qubit 0 is a 1, which means there's a 50% chance that qubit 1 had an X applied to it if qubit 0 was a 1, and a 50% chance that we did nothing to qubit 1, at which point we didn't apply an X. Now, if I go and measure qubit 0 after I've applied my C naught, once I measure, that determines whether or not an X gate was applied on qubit 1 based on what I measured. So there's this weirdness where it almost seems like we're breaking causality by measuring and changing what we did to qubit 1 after the fact. But really, it's not breaking causality. It just has to do with this fact that, truthfully, we are in multiple states at the same time. So it's not that we were in one state and then went back in time and changed to a different one. It's that we were in both states until we measured, and that forced us to pick one. If that seems really confusing, it should. That's just how quantum mechanics is. It's very confusing. Okay. So let's talk about measurement gates. So really what the measurement gate does is it just, like I said earlier about measurement collapse, it measures the qubit states in the Z basis, which is just the 0-1 basis. If you remember back to the first and second lectures, we talked about bases and specifically the Z basis. Now, the thing for measurement, you could measure in different bases, but it's just arbitrarily we decided to pick the Z basis. So like I was saying, when we talked about qubits as being in some probability distribution, you could imagine that if I was in a 50-50 distribution, this is exactly the same as flipping a coin. Before I've measured, the coin is still sort of spinning in the air and we don't know what it's going to be. But after I've measured, the coin has fallen down and I've looked at it and seen whether or not it was heads or tails. Now, when we call measure, we have to call the measure method, and then we pass it two parameters. One is the qubit that we're measuring. That's the first parameter, the ith qubit, where the qubits are indexed in the same way that elements of a list are. So there's the 0th, then the first, then the second. It starts with 0. And then the jth classical bit, which is also indexed in a similar way to lists. So it starts with 0, and goes 0, 1, 2, etc. So you're just saying, I want to measure the ith qubit, and I want to store the thing that I measure in the jth classical bit. And this collapses the state of that measured qubit and any qubits that it's entangled to. Okay, so the last thing that we need to do for our quantum circuit is, now that we've sort of made our quantum circuit object and we've added all the gates that we want to do, we have a couple different options for looking at our quantum circuit and running our quantum circuit. One of them is qc.draw, and it outputs that picture that we saw at the beginning of sort of just what does this quantum circuit look like symbolically. And we just call that a circuit diagram, in the same way that you might draw a regular circuit diagram in sort of regular electrical engineering that just shows the resistors and inductors, etc. And the other thing we can do is visualize transition, which only works for quantum circuits that have a single qubit in them. But it really just shows us what exactly is our circuit doing to our input qubit state. So we have some qubit, and it's like we applied all these gates. It's hard to picture in our head what it's actually doing. So visualize transition, if we have a circuit that's only one qubit, just shows us, hey, we rotate around this, and then we rotate in that direction, and then we spin around. And it's just a nice way to sort of intuitively understand what the circuit is doing to the qubit. Okay, so this is just once again what the circuit diagram looks like. So we made this with qc.draw. So obviously in order to do this, we would have had to make a quantum circuit where we had 3 qubits and 2 classical bits. Then we would have had to add H gates to the qubit 1, and then a C0 between 1 and 2, a C0 between 0 and 1, and an H gate on qubit 0. Then we would have had to add our measurement gates. And then there's a couple other gates over here that are just classically controlled. And the reason they're called classically controlled is because we've already measured. So they're just sort of, they're not quantum like these gates before the measurement. We're not going to talk about these really at all today, so it's okay to just ignore them. Okay, so this is the point in the event where I would have you open up IQX and work on the notebook. We're just going to keep pushing through to the second section, and I'll just get through all the slides, and then I'll kind of walk us through quickly the solution to the notebook, and just explain a little bit about each cell block. And then, once again, if you want to try it on your own, that notebook, as well as the solution notebook, as well as the unsolved notebook, and these slides will all be uploaded to our Discord. Okay, so we're going to talk about really just one more thing today, and that's what you might call parameter gates. So parameter gates are very similar to the gates that we've talked about so far. The only difference is the gates we've talked about before, basically the only parameters they take is what qubit or qubits are involved. So for our single qubit rotations, it was just what qubit are we rotating. For our C0, it was what 2 qubits are we applying the C0 between. But there was no other parameters. So we can also have like parameter gates, which take not only the qubit involved, but some other parameter that tells specifies what the gate does. So classic sort of two examples that we have are what you might call axes rotations, which take two parameters, one angle and one qubit, and a universal gate, which takes four parameters, three angles and one qubit. Now, there are multi-qubit parameter gates. They get complicated really quickly, and it's kind of well beyond the scope of this lecture as well as lecture 4. Maybe we'll talk about them right at the end of lecture 4. But I put a link in this slide to a page on Qiskit that gets more into them. So if you're curious and you want to learn more, you can follow that link. Okay, so let's look at rotations again, but this time the parameter rotations. So again, a rotation is just a rotation around the block sphere of our state. But this time we have an extra parameter to play with, which is the angle. So before, remember, our x, y, z, and h, they all rotated us around different axes, but all of them rotated 180 degrees. So we were always stuck rotating 180 degrees. But you can imagine a situation where maybe you want to rotate 90 degrees. And really, that's what these parameter rotations let you do. So we have Rx, for example, which takes the two parameters, the qubit we're applying it to, and theta, the angle and radians that we're rotating around the x-axis. And you can imagine that if we said Rx of pi radians, where pi radians is equivalent to 180 degrees, this gets us back to the x gate that we talked about before. So you can kind of think of the x, y, z, and h gates as just being special versions that are used a lot, which is why they have their own function in Qiskit, but special versions of these more general rotation gates. And likewise, you can imagine that if we applied an Rx of pi over 2 and then an Rz of pi over 2, that's equivalent to the h. You can also make the h by just rotating around the y-axis by pi over 2 radians. So again, it's just saying that you can make all the gates we've talked about before, the previous rotation gates, with these more general rotation gates. Okay, the last sort of thing we want to talk about is this universal rotation. You also might call it the universal unitary gate. And like I said, it takes four parameters, three angles, and the one qubit that you're applying to. It's still a single qubit gate. Now, the reason it's called the universal rotation or universal unitary is because with this one gate, you can recreate any single qubit gate. Any single qubit gate we've talked about so far, any of the rotations, both the non-parameterized and the parameterized rotations, can be specified with this one gate. Now, the reason to use the other ones versus this gate is because the other ones are easier to think about, especially the parameterized axes rotations, because there's only one parameter. So you know I'm rotating around some axis, and then the parameter just tells you how much. This universal rotation takes three parameters, and it's really just three rotations that happen back to back to back, and it's kind of hard to visualize in your head what the result is. So even though you can use this to make any arbitrary gate, in general, I would say it's more clear and easier to think about to use just the parameterized axes rotations. And with those three parameterized axes rotations, you can also make any unitary. So you can either use the three parameterized rotations to make any arbitrary unitary, or you can use this one gate, the universal rotation, to make any arbitrary unitary. Okay, so this is the second section where we would open up and go through the notebook. So I'll just go ahead and sort of jump over to the notebook now and quickly walk us through what that looks like. Okay, so I'm not going to actually run anything because I'm doing this locally. And so in order to do that, I would have to put in my token, which is associated with my account. And if I did that, obviously, everybody would see my token. So I'll just sort of show you what the solutions look like. So the first couple exercises are just having you get used to making quantum circuits using the quantum circuit command, as well as adding gates. So this is how you add an X gate. Remember, we just call the name of our quantum circuit variable dot, and then the name of the gate we're trying to apply. So QC.X tells us to apply an X gate, and we pass it one parameter, which is just the qubit we're applying the X gate to. And then I've just drawn it, and you see this little nice picture output. Very similar thing for the second exercise, except in this point, we're applying an H gate and a C naught, and then measuring both of them. Now, because the H and the C naught entangle these two qubits, the second measurement is actually sort of not needed. Once we measure one of the qubits, we automatically have collapsed the other qubit as well, because of the nature of the X and the H C naught combination. Those two gates together create qubit entanglement. And then this is just a picture of a histogram showing you the two possible outputs for this circuit and how often we measured each of them when we ran it 1,000 times. So this is all just simulated. It's not on a real quantum computer. But out of the 1,000 times we ran it, about 50% of the time we measured 0, 0. So one of the qubits was a 0, the other one was a 0. And about half the time we measured 1, 1. So again, one of the qubits was a 1 and the other one was a 1 as well. This code, the exact way it works, we'll go a little bit more in detail in the 4th lecture, but also some of it is just kind of boring programming stuff. So for the most part, you can just take this as provided gospel that you just run when you want to see the histogram. And we'll come back and compare this histogram to one that happens later on, where we make it a little bit differently, where we make the same circuit a little bit differently. Okay, so this is just an example of what the circuit might look like if you made a circuit that was 16 qubits big, which is starting to get so big that most physical quantum computers that we have access to through Qiskit, we only get access to IBM's kind of weakest quantum computers. Most of them have 7 or less qubits. So we actually would not be able to run this circuit on a real quantum computer. We can only simulate it. We could run it on a real quantum computer if we had, sort of the highest development researcher privileges with IBM. But for those of you, if any of you here actually have that, you probably don't need to come to this event anyways, because presumably you already know what you're doing. And then the last thing I wanted to show in terms of sort of just general Qiskit knowledge is using this circuit, which is a 1 qubit circuit. But we apply 20 X gates. So remember, the X gate is kind of like our bit flip. It takes us from 0 to 1 and 1 to 0. We apply 20 X gates and see what the output is, and then compare that to applying 21 X gates and seeing what the output is. So we use visualized transition. It's also just this exercise is just an excuse to make you use visualized transition. And we can kind of play this little video of what happens to our sort of state. And basically all that happens is it just keeps flipping back and forth and back and forth and back and forth until the very end, and we end up in the state that we started in. We started in the 0 state, we end up in the 0 state. And that's basically just because the X gate is just flipping our bit. So if we apply the X gate twice, we get back to where we started. So if we apply an even number of X gates in a row, sort of uninterrupted, that's the same as doing nothing. If we apply an odd number of X gates in a row, which we'll see here, this is 21 X gates, it flips back and forth, and we end up in the 1 state. So if we apply an odd number of X gates uninterrupted in a row, it's the same as just applying 1 X gate. Almost never would you ever actually do this. You're applying a lot of gates to get almost no result because it's the same as just doing 1. I just wanted to show you visually why that's true. It makes sense intuitively, but now you have a little video that shows you also that it checks out. Okay, now the second section here is talking about parameterized gates. So the first thing we did is we remade the circuit from part 1.2, which was the H gate and the C naught, except this time, instead of using an H gate, we used our RX-RZ combination, which is equivalent to an H gate, which we just know by, if we look at the block sphere, we get to the same ending vector. If we start at the same starting vector, we get the same ending vector with these 2 gates as we did with the H. And then I'm just going to plot the histogram for it like I did above, and we can see that, again, it's about 50-50. Now, it's a little less like 50-50 in this exact example, but actually that's just because we're randomly sampling it. So we're never really ever going to get exactly 50-50. And this is still well within the margins that we might expect for a 50-50 probability distribution. You can think of it in the same way that if you flip a coin 10 times, it's pretty likely that you'll get 7 of heads and 3 of tails. It's not like you will always have 5 heads, 5 tails, or if you flip it 20 times, 10 heads, 10 tails. It's just that as you flip it more, sort of the standard deviation away from 50 gets smaller and smaller. From 50-50 gets smaller and smaller. Okay, the last 2 gates here are essentially just playing around with the parameterized gates more. The second one, 2.2, just lets you make really any kind of superposition you want. Just make it that's not 50-50. And again, you can just use Rx and Rz. For both 2.1 and 2.2, you can also just use Ry. But I tried to keep it away from Ry because the y-axis has some weirdness of the block sphere, which we talked about at the end of lecture 2. And we can talk about more over Discord if people have questions. But for the most part, Rx and Rz are more nice to think about because they are real and the y-axis is imaginary. So I just made some arbitrary distribution with Rx being a 90-degree rotation and Rz 180-degree. And we can see that I got this probability distribution at the end. I didn't do the math. I don't know what this is supposed to be, but I'm just like, okay, it's very clearly not 50-50. It's skewed over 200. And then same thing. And then I just did a similar sort of random distribution, but this time using the universal gate, which we just make by qc.u. And then again, I just added a C0 and then a measurement just to see what happened. And this was the result of the probability distribution. So you can do the math for all of these and make some probability distribution that you specifically wanted to get. But in this case, I just wanted you to get used to actually running these lines of code and sort of visualizing your results in this histogram. And we'll talk more in the lecture 4 about how to interpret this histogram. But the point of this notebook is not really so that you fully understand how all of these gates work. It's more just to get used to actually running the code, get used to some of the syntax of Qiskit. It's like qc.gate. And then, you apply your gates, you apply your measurement, and then you draw it, or you use the this code here to just simulate it and plot the histogram. And that's sort of the general arc of how every quantum circuit works. Okay, so that's the notebook and that's the slides. Let me hop back over here just to end on this slide here. So if you have any questions, feel free to reach out over Discord. I'd be happy to answer questions about this lecture, as well as I'm sure the other officers would also be happy to. And like I said, our 4th lecture will be on March 1st, which will go more in depth onto some of the Qiskit aspects that are a little more advanced than this one. So hope to see you there. And thanks for sticking around. Have a great rest of your day.